Hello students, how are you? Today we are going to learn applications of a Gauss law. Now what is Gauss law? What is Gauss's law? What is electric flux, etc. in a very detail we have studied already in the previous video session. Now you please watch that. I hope that you have watched that previous session with the notes in your hand, and you have the prior knowledge. You have the prior knowledge of what is Gauss law, what is electric flux, because those things we'll be just using and we'll apply on some aspects in this video lecture. And if you have not done so, you don't proceed with this video lecture, you watch the previous video and come to here, you will understand very nicely. And applications of Gauss law from exam perspective is very important, and we are getting questions from this every year without fail. And one more thing is, if you give nice attention here, whatever is there in the board, not only that much in JEE main advanced, also what concepts we are exploring, you will be in a way masters of application of a Gauss law if you watch very carefully this video and with good attention. Now, in the applications of Gauss law, we will have three applications altogether. One application is regarding square, uniformly charged square. I'm very sorry, uniformly charged sphere. What we are doing is, we will take a uniformly charged sphere, and because of this uniform charge over the sphere, at any point what is the electric field intensity we will calculate. So what we can say, electric field intensity due to a uniformly charged sphere. So in a uniformly charged sphere, we'll apply the Gauss law and we'll calculate electric field at any point due to that uniformly charged sphere. This will be our first application of Gauss law. Now in the second application, we will take a very long straight wire with also uniform charge distribution over it. Okay. Now because of this wire, at any point P, we will calculate again electric field intensity at a point due to a uniformly charged, here in B we'll say uniformly charged long straight wire. Okay. And our third application will be, we will take a very large sheet, infinitely large sheet with uniform charge distribution, and because of that sheet at a particular point P, wherever that point may be, at any point, again our application C application will be electric field intensity due to a uniformly charged infinitely large flat sheet. So how to derive this electric field intensity at a point due to this, these are the three applications at any point we'll see, and depending on that a few numericals also will take up, and this is all the we can think this is all is covered in the applications of a Gauss law. Fine. Okay, so we are taking up the very first application, that is electric field intensity at any point due to a uniformly charged sphere. Okay, now listen very carefully. Understanding is so important that after that many numericals etc. we can do very nicely if the understanding is very clearly in mind. Okay, so we are having a sphere. In 2D I am showing it, it looks like a ring, but it's a sphere, you imagine. Okay. This is the center point, let us say O, and the sphere is uniformly charged. Let us say plus Q charge is given to it, and it's uniformly distributed over the surface. Let us say it is plus Q charge is given to the surface. Now we are going to find out the electric field intensity, where at any point. Electric field intensity at any point due to this uniformly charged sphere we are calculating. Now when we are saying any point, how many possibilities are there? That point may be outside the sphere, that point may be on the surface of the sphere, or that point can be inside the sphere. These three possibilities are there. All the points if you are considering, either it can be out, either it can be on the surface, or it can be inside the sphere. These three possibilities are there. Then we'll say, let us say case 1, is it visible in blue? Case 2 and case 3. Now, how we'll say, instead of writing so many things, so what we can do is, let us say that any point is a P, okay, or should I mention in black only? Let us say that any point is a P, okay, the distance of that point from O, distance of that point from O is a small r, and the distance of this sphere, this radius of this sphere is capital R. Now in these two terms we can say, now what are the cases? If P is outside the sphere, then one case is R is greater than capital R, that is it's outside it. Case 2 is R is equal to R, that is it is on the surface. Case 1 is R is greater than capital R, R is equal to capital R. Or if the point P is inside the sphere, small r is less than capital R. These three conditions are possible, yes or no? Now, let us see systematically one by one. Suppose the point is located where small r is bigger than capital R. We are taking up a case 1. We are taking up a case 1. Okay. Now in the case 1, what will be, I hope that you are having the Gauss law in mind already. Now what we have, the total flux according to Gauss law, total flux is equal to, I am writing directly this we had derived last session, the closed surface integral of, if this is the surface, Gaussian surface, closed surface integral of E dot ds, which is equal to 1 by 4 pi epsilon naught, the charge enclosed in the surface. This is Gauss law, right? But what is this, a surface? The surface is not the surface of the sphere. The sphere is the original one. There is some material on this and it is uniformly charged, is spread on this. But whatever point is there, taking that point, whatever point P we are considering where we are going to measure the electric field, taking that point, we can imagine one closed surface. That imaginary closed surface is called Gaussian surface, and for that surface the Gauss law is applicable, and from that surface any one small surface we are taking, that is ds, right? So to draw it, I am just I require some space, so I am erasing it. You have this in memory, right? Okay. Now what I'll do is, see, taking this point P, we can imagine one surface, closed surface, which is the Gaussian surface. Is it clear? It's a closed surface, Gaussian surface. Now here I am writing again, phi is equal to, now let us say that the distance from O is R, we have considered already. Phi total is equal to closed surface integral of E dot ds, which is equal to 1 by epsilon naught times the charge enclosed in the surface. Fine. Now see, this is equal to E dot ds. What is the direction of E? Isn't it away from the positive? So it is outward E. And what is the direction of S? Now on this surface, in the red what you are seeing, on this surface, any small area you take, that will be outward normal. So at a particular point, the direction of the area also will be in the same direction. So theta is equal to how much? 0 degree. So E ds cos 0 is cos 0 is 1. So it became E ds, yes or no? Closed integral of E ds is equal to q by epsilon naught, yes or no? Implies that E is a constant, take common, which we are going to calculate finally. E within the closed surface integral ds is equal to q by epsilon naught. Implies that what is ds? ds if we take out, it is totally S, surface area of the Gaussian surface, and isn't that 4 pi r square? Implies that E multiplied by 4 pi r square is equal to q by epsilon naught. Implies that E is equal to, bring this 4 pi r square down, 1 by 4 pi epsilon naught q by r square. Is it clear till here? See, the electric field intensity at a point of the first application also, 3 cases are there. The first case, when small r is greater than capital R, that's why the point is outside the sphere. For that case, we have derived E is equal to 1 by 4 pi epsilon naught q by r square. Is it clear? Now see, let's make it very simple. Now see, if I bring this point P nearer and nearer, what are the possibilities? One possibility is P will be lying on the surface, yes or no? Which will be the case 2, when P will be lying on the surface. Fine. Now, to define that, let me erase the outer Gaussian surface, which was for case 1. Now I am taking off case 2. Now, if the point P is here, then don't you think that R, small r is the same as a capital R? That's the case 2, right? Now, see, please understand, what will be the difference? Again, we'll start in the new derivation. I'm not writing that again because it will be a repetition of the same thing. That repetition only will create confusion. That's why I'm saying, what I'll write? Phi is equal to closed surface integral of E dot ds is equal to q by epsilon naught. Implies that, see, in books it will be written again, and in note also you have to write again for case 2. But since this will be a mere repetition with a small change, I am explaining it here only. Now see, phi is equal to closed surface integral of E dot ds is equal to q by epsilon naught. Now E ds are in the same direction for the same logic. E is outside only. And at that point, whatever is the small area ds you are considering, that also is outside only. So angle between them is 0, cos 0 equal to 1. Again, this line also exactly same. Here implies that E closed surface integral of a ds q by epsilon naught, this line also is same. Then what is 4 pi r square? Here r became capital R, isn't it? Here instead of small r, we will write capital R. That only is the change. So what is the change? I am writing in red so that you will understand nicely. Capital R instead of small r, only in this, the second case. Now I am explaining the second case. This is over. Second case I am explaining. Here only instead of small r, one capital R will come, because r became capital R is equal to q by r. Therefore E is equal to 4 pi epsilon naught. Here also this r square will come down, right? So small r became capital R. That is the only change in the case 2. So what we understood, E is equal to 1 by 4 pi epsilon naught q by r square. This was same. So when r square is in the denominator. So if r is less, electric field intensity will be more. So when r become less from some distance, and when it become capital R, 1 by 4 pi, this will be very big. Yes or no? So this is very big. If it is small r was there, since small r was earlier bigger than capital R in case 1, it was less. Now it's more. What happens if r is still reduced? That means if r is reduced, then capital R, P will come inside the sphere. Yes or no? We will take case 3 now. If we take case 3, see, it is very simple to understand now. Now P came inside, R is smaller than this R. If the distance of the point P, that is small r, is less than R, that is point P is inside the sphere now. So it is the third case we are taking, R is less than R. Then it is very simple to understand. Now again you start applying the same concept. Flux according to Gauss theorem is phi is equal to closed integral of E dot ds is equal to q by epsilon naught, and why E ds are along the same direction, that's why theta between them is 0. So E ds cos theta is cos 0 is equal to 1. So E ds simply second, this is same, E ds is equal to q by epsilon naught. Now it is not even required this much. What is the q? This is 1 by epsilon naught times the charge enclosed in the surface. Yes or no? What is the charge enclosed in the surface? Now taking P, if we'll imagine one Gaussian surface here. Now within this surface, don't you think that charge is 0, because charge is in the outer surface of the shell only. So inside this, at any point P, taking that point P, if we'll imagine one Gaussian surface, then definitely this q will be 0, isn't it? So therefore phi is equal to 0 by epsilon naught is 0 simply. So this case also is over. Now if we'll write, so the case 1 is, in case 1 E is equal to 1 by 4 pi epsilon naught q by r square. In case 2 E is equal to 1 by 4 pi epsilon naught q by capital R square, right? And in case 3 E is simply equal to 0, right? Very clear? Now there's a question that represent graphically or represent pictorially the electric field intensity at any point due to a uniformly charged sphere. How that will look like? These three, I am showing it here, or let me not erase it, I will show it without erasing. See, now I will be taking along x-axis, I will take R, along y-axis, perpendicular axis, I will take E. Okay. Now, if R is constantly increasing, what happens to E? Let us see. Now see, at when R, capital R is equal to 0, what is E? That is electric field intensity 0. Here electric field intensity 0, 0, 0, 0. Here 0 only till the point is inside the sphere. E is equal to 0. But when it becomes E, second case, when the distance of the point P from the center, that is small r, becomes equal to R, then E becomes this much. Okay, between these two, which is bigger? Now see, this capital R is a big, this capital R is in the denominator. So when this capital R is a maximum, E will be minimum, or when the capital R is minimum, E is maximum. Now see, here till here electric field was 0. After that electric field is a constant. See, in this figure E is equal to 1 by 4 pi epsilon is a constant. What is the charge given to the sphere? That's constant. And R, how big is the sphere? In this, between the sphere is not changing its volume, it's remaining same throughout the experiment. So R is a constant. So this entire thing is a constant. That constant thing happens when small r increases, when small r becomes equal to capital R. When small r becomes equal to capital R, till that this E remains till that E remains 0. So the graph I am showing by black line. And when R becomes small r becomes capital R, at that point at R, E becomes some constant value, right? That constant value is equal to 1 by 4 pi epsilon naught q by r square. But after that, what happens if we take the point P away from the sphere? This small r is increasing. Since this is in the denominator, as the r is increasing, E will fall down. So it will come like this. Exponentially, it will fall. So after this, the graph will be like this. Okay. So till r becomes r, E is equal to 0. In this region, E is equal to 0. When r become capital R, E is equal to maximum, and the value is equal to 1 by 4 pi epsilon naught q by capital R square. This is the value. And after that, E is directly proportional to 1 by R square, or E is inversely proportional to the square, inversely proportional to the square of the distance of the point from the center of the sphere. Clear? So graphically, if it represent, this will look like this. Now we are going to discuss the second application of a Gauss law. First application we are very clear about, right? The first application was regarding finding out the electric field intensity at any point due to a uniformly charged spherical sphere. Application A. Second application, the same thing, electrical field intensity at any point due to a long straight wire with uniform charge density lambda. Uniform charge density lambda. Charge density, you remember, if there is a line, uniform charge is given, linear charge density symbol is lambda. If there is a sheet and there is uniform charge density, the symbol is sigma we took. And if there is a cube where uniform charge density, charge is uniformly distributed all over, there we said the volumetric charge distribution, volumetric charge density symbol rho we took. Remember this we had discussed already. This was just a recap, and so here it is a rough. Just remind this. Now the application is if there is a line with uniform charge density lambda, due to this, at any point, what is the electric field intensity we are going to calculate. This is the second application. Fine. Now before proceeding, I'd like to make you understand why the electric field lines from a line like this, from a straight wire like this, is always perpendicular to the wire. Why that is so I am going to explain. Now let us say that P is any point. Then if we will take any point left to this intersection, let us say this point is N, and left to this at any point, I have taken one point here. Now let us say this is A. Now how much is AN? Taking same distance, and there will be another point at B. AN is equal to BN, let us say. Now what is the electric field intensity at P due to A? If you want to find, we imagine one unit positive charge at P, and then due to A there is one E in this direction. why it is a plus, and this charge also is plus, so that it will be repelling force, right? And due to B also there will be a force, and that is E only, because since AN is equal to BN, AP also will be equal to BP. And what is the electric field line, electric field strength? The formula is 1 by 4 pi epsilon naught Q, whatever is the charge, divided by AP square, here BP square. Since AP is equal to BP, E also will be same, right? Let us say this angle is theta. Since AN is equal to BN, this angle also is theta. And since this is theta, this opposite angle is theta, and opposite angle of BPN, this also is theta. Now, the this E can be resolved into two components, right? This is E cos theta, and this is E sin theta. Now, this E also can be resolved into two components. So, E sin theta and E cos theta in the same direction. E cos theta was there and another. So, it is 2E cos theta. You got or no? Now, this E sin theta is equal in the opposite equal in the magnitude and the opposite in direction. That's why they will be cancelled out by each other. That's why all these components will be cancelled. Only the perpendicular components are getting added up. Now, we have taken any 2 points, right? For another point here, same distance, another point here will be there. For here, here will be there. For here, here, a similar point will be there. For all the pairs of like that, all the horizontal components will be cancelled out. Only vertical components will be added up, added up, added up. That's why, because of the entire wire, what is the electric field intensity at a point P, if we find out, that must be only perpendicular to the perpendicular to the line, long straight wire, which is a uniform, which is there with the uniform charge density. Density is given lambda. Now, the thing is, P is any point like that. If we take the point here, 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 anywhere, it will be perpendicular, perpendicular, perpendicular only. So, the field line, since it's going from positive, all the field lines will be perpendicular to the line. All the field lines will be perpendicular. Like this 2E cos theta, like that, all the field lines will be perpendicular. So, before proceeding for this application of a Gauss law, I just proved here that the electric field line due to a long straight wire with some charge will be always perpendicular to the straight wire only. This much understanding is clear, right? With this understanding, we will proceed with the second application. So, we imagine a long straight wire with uniform charge distribution. Now, we will find out the electric field intensity here due to this long straight wire having uniform charge density lambda. But while doing so, we will apply the Gauss law. From that sense only, it will become an application of a Gauss law. To do that, what we'll do, we will imagine a Gaussian surface. Gaussian surface is a closed surface enclosing some charge, right? Gaussian surface, on the surface of which the P should lie. So, taking the P here, let us imagine a cylinder . This cylinder, what I have written in a blue, is an imaginary one. It's not an actual cylinder with some material, or it is not made. We are imagining it. One cylinder is there. Okay, we have imagined. Now, how much charge is enclosed in the cylinder? Charge enclosed is equal to, let us say, Q. Don't you think that is equal to lambda into L, if L is the length of the cylinder? Lambda is the length, lambda is the charge per unit length, that multiplied by the total charge, right? So, Q, the charge, how much charge is enclosed in the cylinder? The charge contained in the L length of the cylinder, L length of the straight wire. And that straight wire's density, charge density is given in the question to be lambda. So, lambda into L is the charge present inside the closed surface, which is a cylinder. Now let us say that the radius of this cylinder is r. Okay, length, radius of the cylinder is r. Good. Now see, the point P is contained here. There will be one small area ds, we say. Now on the surface of the cylinder, one small area we have taken ds. If it will show vector, then ds and this and get its unit vector along this direction. Now E here also is in upward direction, right? In fact, so many lines are there like this. Now how many surfaces are there of the cylinder? This side one flat surface, let us say this surface is S1. This side one flat surface, this is S2, and two flat surfaces and one curved surface. Let us say this is S3. Understood or not? Of the cylinder, three surfaces. These three surfaces are making it a closed surface, right? Now, what is the total flux is equal to flux through S1 plus flux through S2 plus flux through S3. So this is the total flux throughout the closed surface, which is a cylinder, throughout the total cylinder. Now this is equal to, now see, S1, will there be any electric field line which will be touching S1? See, all these electric field lines are moving in the upward direction, right? This side also, this side also. Now this, though it is showing some thickness, but this is actually a cylinder like this. You imagine one cylinder like this. Okay, now here electric field line is going upward, here it's going upward. So only this surface is touched by no field line. Don't you understand? It's touched by no field line. So what we can conclude, that no field line is touched with this surface area, means electric flux must be zero. Do you understand? It's by definition of electric flux. Otherwise, we can mathematically also calculate phi S1. This is equal to E dot ds, right? Closed surface integral about S1. Then mathematically what we can say, it's a closed surface integral about S2 E dot ds, and for S3 phi S3 electric flux about S3, what we can say, closed E dot ds about S3 we can find out. Then see about E dot ds. What is E? What is the angle between E and ds for S1? For S1, its area is along this direction, right? And E is in upward direction. So what is the angle? E is in upward direction. What is the angle between this? 90 degree. So this will be E ds cos 90. Cos 90 is 0. That's why this part will become 0, right? Now mathematically we can conclude that this part will be 0. But otherwise also from common sense we can conclude that S1, one field line will pass like this, one field line will pass like this. So this surface S1 only is cut by no electric field line at all. So from common sense also we can say 0. What about S2? Don't you think that it is same? The direction of this area is towards left and E is in this direction. So again angle between E and S2 and E is 90 degree. So E ds here also, E ds cos 90 will be 0 only, plus only S3. Don't you think that from every direction, if this is the line, from here in every direction whatever line is going out, that will be perpendicular to this. So that will be hitting the cylinder which is covering it, So field line which is coming from the line also will be perpendicular to the surface of the curved surface of the cylinder, yes or no? Now see, all the field lines which are going, which is perpendicular, all the field lines which are going, that is along, that is perpendicular to the surface, curved surface, S3. So about S3, we'll say E dot ds integration S3, right? So that is equal to E What is the area of S3? Can I say 2 pi r multiplied by L? Isn't it the area of S3? 2 pi r multiplied by L. So phi total is equal to E into 2 pi r into L. This one we got by pure mathematical derivation. We haven't applied the Gauss law till now. Let us make some drama. Make it equation 1. And as per Gauss law, now applying Gauss law. According to Gauss law, phi total is equal to how much? Phi total is equal to the total charge enclosed in this surface by epsilon naught, 1 by epsilon naught times 1 by epsilon naught times the total charge, and total charge if it is Q, that is equal to lambda into dl, yes or no? Lambda into L, yes or no? Lambda into L. Now let us make it equation 2. Now see, from equation 1, phi total is equal to something we have derived. Equation 2, phi total is equal to something we got from applying Gauss law. So from equation 1 and 2 we can equate these two, yes or no? So to write that, I am just erasing this part. You have noted down, right? If you have not noted down, you just pause the video and note down that first. After that I am writing over here. So from here I am continuing. From equation 1 and equation 2, just equate those two. E multiplied by 2 pi r into L is equal to lambda L by epsilon naught. L got cancelled. Implies that E is equal to, this comes down 1 by 2 pi epsilon naught lambda by r. Now we know that 1 by 4 pi epsilon naught is equal to 9 into 10 to the 9. It's a good figure we are having. So just to make it easy from mathematical perspective, numerical perspective, or E is equal to, we multiplied 2 in the numerator and 2 in the denominator, just to make it 1 by 4 pi epsilon naught. 1 by 4 pi epsilon naught 2 lambda by r. Is it very clear to everybody? Now see, the examiner can play around with 1 by 4 pi epsilon naught is 9 into 10 to the 9, you know. So what is the charge density may be given, and with for this charge, if a uniform charge density of a long straight wire is lambda is given, then what will be the electric field at a distance of 5 mm or 10 mm? If some r is given, lambda r is given, you will just put these things and you will get the, calculate the answer. And what will be the unit of E? Newton per coulomb, right? E is equal to F by Q, you remember. So whatever comes, those many Newton per coulomb. Is it clear to everybody? Now we'll discuss the third application of a Gauss law, which is again electric field intensity at a point at a certain distance from a infinitely large flat sheet with uniform charge density, sigma. So electric field intensity at a point at a certain distance from an infinitely large flat sheet with uniform charge density sigma is the next application. Now, suppose I am having a sheet like this, and this is a very huge, very large flat sheet, imagine, and the charge is distributed uniformly all over it. Now, at any point from here, if charge is distributed all over it, at any point from here, any p, at that point, due to this flat sheet, what is the electric field intensity? That is, at that point, if I'll keep one unit positive charge, how much force that will experience. Deriving that is the application of third application of a Gauss law. Now, let us imagine there is a sheet, large sheet, infinitely large sheet with uniform charge distribution, and the charge density is given to be sigma. Okay, and at a point P, we need to find out the electric field intensity due to this sheet. What we'll do, again we'll apply Gauss law, and to apply Gauss law we have to consider a closed surface which should contain P, right? Here we'll imagine a closed surface, closed, that also will be cylindrical surface, and the flat surface contains a P. Let us imagine a surface like this, from here to flat sheet to this, at a distance r from the sheet. So this is r, this side also is r. Imagine a sheet like this, and at point P we are going to find out the electric field intensity. Now again, what we are going to do, our master stroke all the time is, what we are doing, total flux about it is equal to closed integral of E dot ds is equal to Q, charge enclosed in the surface. Now think that how much at one plane only the cylinder is cutting it, right? And that is this much plane, and in that how much charge is contained, that much charge only is contained in the closed surface, yes or no? And how much is charge, that if total charge, that is total charge contained in that closed sphere is equal to sigma multiplied by, see how much is the total charge, this is sigma, means what, charge per, sigma is equal to charge per s, yes or no? Now let us say this S is one assumption. Let us say this, how many surfaces are there of the cylinder? Let us say this is S1, this side is S2, and the curved surface is S3. Let us say. Now let us say S1 is equal to S2. Since this is a uniform cylinder we have imagined, so S1 is same as S2 is equal to S, let us say. Then sigma is equal to Q by S. So Q is equal to sigma into S, right? Sigma into S. Clear? Now phi is equal to E dot ds is equal to how much? The charge Q by 1 by epsilon naught times the charge, right? Q by epsilon naught, you remember this is the Gauss law. So sigma S by epsilon naught, because Q is equal to sigma S. Keep it aside. This is the application of Gauss law. From this we will find out E. Now remember again the same same concept, like EDS per S1, EDS per S2 plus EDS per S3. So phi S1 plus phi S2 plus phi S3 is equal to total flux is equal to. Now see S1, from how the electric field lines will be, direction of electric field lines will be from plus, it will go away, yes or no? These are the electric field lines, yes or no? Now like that, from this side also it will go like this, electric field lines. Yes or no? Now, since these electric fields are cutting S1 and S2, here only there will be some flux linked with the surface. But this time, the entire curved surface S3 is not touched with any field line, right? That's why phi S3 will be 0 this time. So this is equal to, let me write, from here I am writing. So this is equal to phi S1 is equal to how much? E dot ds plus E dot ds for S1, ES. So E ds S1 plus E ds S2 plus S3 0, because no field line is touching S3 here. So since this ds for S1 also will be S only and for S2 also will be S only, same area. So ES plus ES is equal to 2ES. Now again let us make some drama. This phi is equal to sigma s by epsilon naught. This we got from application of Gauss law, and phi is equal to this we got from just mathematical derivation. Now from equation 1 and 2 again, from equation 1 and 2, what we can say? 2ES is equal to sigma S by epsilon naught. S got cancelled, implies that E is equal to epsilon by 2, I'm very sorry, E is equal to sigma by 2 epsilon naught. Is it clear to everybody till now? Now, the thing is, here there is a little understanding, and there is a special case. What happens if there's a long sheet is there that's having some thickness as well? See, this sheet is having some thickness as well, right? Now, this side if a charge q is there, and this side also charge q is there with the same equal distribution of sigma only, then what will happen? Now there is a infinitely large flat sheet, how we discussed now, and there is a thickness to it. Okay, there's a thickness to the sheet. So in this side also there is uniform charge distribution, and the opposite side also there is same charge distribution, means the charge density is same, let us say. Now at a point P we are going to calculate the electric field. Now imagine thinking that since this is infinitely large, this thickness doesn't matter, right? So because of these two plates, let us say plate A and plate B, let us say. So because of plate A, here you are calculating unit positive. If you are calculating electric field intensity here, you are considering one unit positive charge here. So plate A will repel it with certain E, yes or no? And what is that E? If it's one plate, we have calculated that sigma by 2 epsilon naught. Now plate B also will repel it with some E, and that E will also be epsilon by 2 sigma by 2 epsilon naught. Therefore E net will be equal to sigma by 2 epsilon naught plus sigma by 2 epsilon naught is equal to sigma by epsilon naught. So therefore E is equal to sigma by epsilon naught. So this is one of the corollary of above case, corollary of the third application, where infinite flat sheet has a finite thickness, or let me say has a small thickness. So if it is a small thickness, then E is equal to sigma by epsilon naught. Okay. Now this is corollary 1. Then there can be another corollary where please try to understand, it is similar only. The thing is, both the sides are charged by induction. That means if one side is plus, the other side is a minus. One side is positively charged, the other side is negatively charged. Then what will happen in the same case? Now see, because of B, this will be pushed, right? But because of A, this will be pulled with the same forces, or no? So the net force will be 0. So net force on unit positive charge is 0, means E is equal to 0. But it is outside. Remember, if P is kept inside the fields, I am showing like this. This is positive side, this is negative side, this is a positively charged plate, this is B, this is A. Okay. Now your point P is inside, in between these two plates. Then remember, this is plus 1 charge. So because of B, this will be pushed with force E, and because of A also this will be pulled, means in the same direction E. So again, if it is like oppositely charged, the plates are oppositely charged and the point is placed in between them, that is the same case as E net is equal to sigma by 2 epsilon naught plus sigma by 2 epsilon naught, that is E is equal to sigma by epsilon naught. Is it clear? So basically, depending on the question or where it is placed, we have to take that decision. If both are positively charged, then if outside the plate point is taken, then electric field strength is added up. But if both the plates are oppositely charged and the point is taken in between them, then also electric field is added up. So all the questions, all the concepts are clear till now. Hope you have noted the questions already. The first question says, a metallic spherical shell has an inner radius R1 and outer radius R2. Let us say this is the sphere, which is solid. It's not completely solid, but some thickness is there. It's having one inner radius equal to R1 and it's having one outer radius equal to R2. A charge plus Q is placed at the center of the shell. What will be the surface charge density on the inner surface and on the outer surface of the shell? Surface charge density. Surface charge density is a symbol sigma. That is equal to how much is the question? For 2 bits, inner surface, and second bit, the question is same, what is the surface charge density for outer surface? Right? This is very simple. Now see, plus Q charge is given. It says to the inner charge plus q is placed at the center of the cell. Okay. So at the center of the cell plus q charge is given. In the question q is given, if q is given it is plus q only. Okay. Now there must be some induction, right? If this plus q is there in the inside inner surface, so minus charge will be developed and that will be minus of q, yes or no? And since of this plate inside became plus, outside by induction property plus charge will be developed, yes or no? And that plus will be plus of q, yes or no? Now the surface charge density sigma for inner surface. What is the meaning of surface charge density? The charge contained per unit area. For inner surface, how much charge is there? Minus q. Minus q divided by, what is the area of inner surface? Inner surface, radius of inner surface is r1. So inner surface 4 pi r1 square. 4 pi r square is the surface area, right? Inner surface area. So minus q by 4 pi r square. Like that, what is the sigma for outer surface? Then outer surface is plus q, right? Plus q divided by 4 pi r2 square. For outer surface, radius is r. As simple as this. Clear? Now taking up the second question. Two charges of magnitudes minus 2q and plus q are located at point A0 and 4A0 respectively. What is the electric flux due to these charges through a sphere of a radius 3a with its center at the origin? Now what it says is, there are 2 points A0. Let us say this point is A0 and this point is 4 times 4A0. There are 2 points. Minus 2q and plus q are located at points A0 and 4. Minus 2q and plus q. Here there is minus 2q and here plus q. Charges are placed. Now the question is, what is the electric flux due to these charges through a sphere of a radius 3a with its center at the origin? Okay, origin is this one. With this center 3a is less than 4a, right? Somewhere here 1 2 3, let us say here it is 3a. With this much of radius, if we'll imagine a sphere, okay, what is the electric flux through that sphere is the question. It's very simple. What is electric flux? Phi is equal to q by epsilon naught, where q is the charge enclosed in the surface. Now in the surface, how much charge is enclosed? Only minus 2q charge is there, right? This is outside, this plus q. Since this length is 3a, the radius is 3a is given in the question. So since this is 3a, this plus q lies outside it. We are not concerned with that. Only minus 2q charge is included in the sphere. That's why the total charge is equal to minus 2q divided by epsilon naught is the answer to this. Now let us take the third question, which says a small conducting sphere of radius r carrying a charge plus q is surrounded by a large concentric conducting shell of radius capital R on which a charge plus q, capital Q is placed. There is a small sphere of radius small r carrying a charge plus q plus small q. Is surrounded by a large concentric sphere of radius capital R, of radius capital R, on which that also is given plus capital Q charge, capital Q. Using Gauss law, derive the expression for the electric field at a point x. Using Gauss law, derive expression for electric field at a point x, but where that point x is lying, there are again two cases are given. Between the sphere and the shell, between the sphere and the shell, that is in between here somewhere x is there, that point P is there, where we can say x is greater than small r, x is greater than small r but less than capital R, right? And second bit is outside the sphere. So we will calculate electric field intensity, electric field intensity at any point P between the sphere and the shell once. So P is somewhere here. For first bit I am saying, this one we are taking up, okay? This one we are taking up. So if this is point P, it is saying the distance of the point from the center is, let us say, x, okay? Now with the point P, let us imagine one Gaussian surface, taking x as the radius, we will find out the Gaussian surface. Fine. Now between the sphere, the P is between the sphere and the shell. So x is greater than small r and less than capital R. Fine. So here what we are going to find out, electric field intensity at this point we have to find out. Now according to Gauss law, what is electric field intensity or what is electric flux is equal to closed surface integral of E dot ds, which is equal to the charge enclosed. Now charge enclosed in this sphere which contains P, that is the red, in red I have said, that is how much charge is enclosed, small q divided by epsilon naught, right? Implies that again E and ds are in the same direction. I have explained you the concept, that's why it's EDS, because cos 0 is equal to 1. So E is a constant, take out closed surface integral of ds is equal to q by epsilon naught, yes or no? Implies that E multiplied by ds, this is a total. Now from here to here, how much is the distance? X, isn't it? From here to here, this much distance, this radius of this red sphere or imaginary Gaussian surface. Red is a Gaussian surface, it's not actual spherical surface, it's a Gaussian surface, we have imagined it. So ds is equal to how much? 4 pi x square is equal to q by epsilon naught. Is it visible? Implies that E is equal to, bring this down, 1 by 4 pi epsilon naught small q by x square. Clear? So this is the solution for the bit 1. E is equal to 1 by 4 pi epsilon naught small q by x square. Now coming to the second bit, when the point P is outside the sphere. Now forget about this sphere. Now the small p, this P, point P is outside the sphere. Okay, so let us say that it is this side I am showing, P is here. Now the distance of a point P from the center is equal to, let us say, x dash. Now x we had taken in the for the first bit, let us say this x dash. Now for here again, what is E? Like this, if we'll find out directly, we can find out, but applying Gauss theorem, what we'll say, phi. See, this part all the time we are just repeating, right? So just you dictate, or in a video lecture you cannot respond, but you simultaneously think with me. So closed integral with the closed integral about the surface is equal to E dot ds, that is equal to total charge enclosed in the surface. Now what is the total charge enclosed in the surface? Now taking this P, you imagine a closed surface having P on its surface. So how much charge is enclosed in this round Gaussian surface? Capital Q also is there, small q also is there, yes or no? That is why is the total charge, capital Q plus small q divided by epsilon naught. As simple as this. So here what was the difference? Here Q by epsilon naught was there. Here Q plus capital Q came. That's the difference. Implies that E multiplied by, let us say this x dash 4 pi x dash square. X dash square is equal to Q plus Q by epsilon naught. Therefore E is equal to, take it down, 1 by 4 pi epsilon naught Q plus Q divided by x dash square. Got? This is the solution. Now the next two questions, question 4 and 5, are purely theoretical questions, and you just rewind the video, you can find out the exact answer to those questions. And also I have provided you the notes, and you will be getting the exact answers there. But my video lecture will be enough to capture all those ideas required for that. So you rewind, and whatever we have discussed, those things exactly, the applications, 3 applications of a Gauss law we have studied, right? The application B and C are just the answers to question number 4 and 5 respectively. So this class become very helpful to you all, I hope, and all the questions, comments and suggestions are highly welcome. And if you have some doubts still left, you send me various media there, right? You can give me in the comment section, or you can just send me in WhatsApp. So thank you everybody.